Hello, welcome to this presentation of my final year project, PID Controller Simulator. The project focuses on developing an online interactive PID controller simulation in the context of it being an educational tool for students of the DTO 2-1A programme. Given the context of many students having to study from home in the last year, resources that aid remote learning are even more important. Online simulators that can replicate or enhance a student's learning experience of a laboratory are therefore very valuable as an educational tool. This project has been applied to temperature control, where the user gets to investigate PID control in relation to managing the temperature of the liquid in this tank, in response to changes in the desired value and in terms of the disturbances. This project had 5 main phases: planning, design, implementation, testing, and completion. These will be discussed in detail further in the presentation, but first we're going to dive into a quick demonstration of the PID controller simulator. So, upon loading the webpage, you can see the 4 main sections of the screen, with system visuals in the top left, system plot in the top right, block diagram in the bottom left, and user entry in the bottom right. Each of these sections have their names indicated in the top corner of their section, alongside a help button indicated by a question mark, which offers additional information for that section. There are some quick introductory instructions outlining the PID controller simulator at the top of the screen and indicating that further help is available in each of the help buttons. This PID controller simulator allows the user to enter values for control parameters such as the proportional gain Kp, integral gain Ki, and derivative gain Kd. These values can be adjusted in the user entry section using the sliders as demonstrated here. These values can also be set by manually entering a value by clicking on the white box displaying the value, which prompts the user to enter a new value. This then updates the slider position to reflect the new value. In the case where the user attempts to enter a value beyond that current control parameter's range, such as setting Kp to 30, a warning message comes up and indicates the correct value for that control parameter. You may notice that as sliders move, if the control parameter is 0, such as setting Kp to 0 here, the P block in the block diagram section has now been greyed out to indicate to the user that this control parameter is not affecting the output of the system. This may help highlight the distinction between P, PI, and PID controllers, and so on. The block diagram section also includes a toggle button, which displays the Laplace representation of the individual block's transfer functions. As part of a PID controller simulator, setting the set point is important, and this can be done again through the slider or manually entering a value. This can also be done by dragging the red arrow on the tank to the new desired value, which is also reflected on the slider. 2 other key sliders are the window and heater slider. These can be changed by interaction with the window and heater in the system visual section. They are used to represent disturbances to the system. The concept being that the open window, the more open it is, the colder the air in the room, which would act as the negative disturbance on the system. The heater is used to represent a positive disturbance. As the heater gets closer to being fully or 100% turned on, it is at its strongest effect in terms of disturbance on the system. Following on from this, the disturbance time slider is used to set the time at which the disturbance occurs, which can range from 0 to 120 seconds. The end of the simulation time, meaning the disturbance has no effect on the system output in the time frame of this simulator, if set to 120 seconds. To demonstrate, with these control parameters, I can hit the Update Plot button, which has since turned orange to indicate that the control parameters have been changed since the last time the plot was plotted, and a new plot can be generated. This graphs the system output here in response to a change in input after a short loading period. Now I'll change the disturbance time so the effect of the disturbances on the system can be seen in the plot and updated again. This shows the response to a change in input and the disturbance response. Finally, the last slider is noise. which can be adjusted to have a magnitude between 0% and 100% of the value of the set point. Having adjusted it here, the update plot button has again turned orange, so I'll update the plot. And now I have a noisy output. Jumping back into the presentation, in terms of planning in this project, this involved the scheduling of work in each of the stages of the project. A lot of project management was done using Notion, such as the schedule as shown here. It also involved research into the system that the PID controller would be applied to, whether it be temperature, level, speed, etc. I also had to develop my own skills using graphics editing software such as Inkscape and apply previous coding skills to new coding languages to me personally, JavaScript and HTML. The design stage involved detailing a design of the system chosen to model PID control. The original sketch I drew is shown here. Also, designing the layout of the website, as shown here, which was carefully chosen to have high colour contrast using dark blue text on warm tone background to be more accessible with those with dyslexia and reduce eye strain. Also, a survey was carried out of DTO2A students and control lecturers asking for their feedback and input on design decisions in this project. Based off the participants' responses, the initial response to the design was quite positive, and the most common descriptors for the user interface was that it was simple, clear, and understandable. As part of the input into design decisions, participants were asked to give their preference for block diagram options and slider options. There was a clear majority in the block diagram option for having the breakdown of the controller into P, I, and D blocks. In terms of slider options, there wasn't a clear preference, but since there was a slight majority for horizontal sliders, and uniform design and consistency is more intuitive and accessible, the final design includes the horizontal sliders. The implementation stage involved creating the final scalable vector graphic or SVG image, coding the functionality of a PID controller in JavaScript without any inbuilt functions and graphing that output. It also involved developing the interactive features of the simulator shown in the demonstration. To model the PID controller response, the controller transfer function had to be approximated as a proper transfer function in terms of KP, KI, and KD in order to use the bilinear transform. The graph here shows the step response of the original PID controller as the blue line and the PID controller model as a proper transfer function in red X's showing that they match. So, implementing the bilinear transform meant that the transfer function could be represented as a difference equation, which can be implemented in JavaScript. The step response here shows the output of the bilinear transform using the built-in MATLAB functions in blue and using the difference equation in red. The implementation of the graphing involved two methods, one of which you saw in the demonstration, involving plotting over a fixed period of time and using the disturbance time to input when disturbances begin to affect the system. An alternative method that was investigated was plotting the system in real time using an open source JavaScript library called Plotly. I have a quick video here explaining how this would work using random data. So as you can see, it begins plotting data live and has tools which allow the user to pan, adjust their view, zoom in, examine data points, and also reset to the original view. Moving on to testing, MATLAB is used at many stages for testing, such as determining the range of the control parameters KP, KI, and KD using the PID tuner application in MATLAB. The effects of disturbances on the system were also investigated to give an indication of a suitable magnitude of disturbances that will have a visible impact on the output of the plot. MATLAB was also used to test the limitations of the graph axis for the plot of the output, getting the minimum and maximum amplitudes, as well as the time frame of the plot by investigating the responses at the extremes of each of the control parameters in all possible combinations. Testing was also carried out on various browsers, although Chrome was the dominant browser used during the development of the project, as it's the most popular browser in terms of market share, which was also reflected in the browsers used by participants in the survey. Chrome and Edge performed well, with one known issue where if the slider is dragged too quickly, it can highlight all text on screen. Firefox also performed well overall with only a few minor issues. Safari did not perform as well, with the sliders not working as expected. In terms of feedback of the user experience survey, most reactions to the online simulator were positive and said that the online PID simulator was intuitive to use. Participants were also asked how useful this PID controller simulator would be as a learning tool for control, with the majority of responses indicating that it would at least be somewhat useful and up to extremely useful. When looking at the subset of participants who indicated that control was very relevant to their area of education, all members of that subject responded between somewhat useful and extremely useful, with a clear majority responding very useful. In conclusion, the main objective of developing an online interactive PID controller simulator was achieved. It has been evaluated by students and staff of DTO21A with a largely positive response and has been deemed to be useful as a learning tool for control. However, there are also limitations of the project that must be discussed, such as the limited range of values for control parameters, like KP can only be a value between 0 and 20. Also the fact that this project is only designed to work on desktop browsers and not designed to work on mobile platforms. It also has variations in performance in the different browsing platforms tested. Hence, in future work, I would like to address some of these limitations and make improvements to the current PID controller simulator. One improvement could be improving the system plot, having it update automatically or preferably plot in real time as previously discussed. Furthermore, a frequency domain plot would also be a useful addition, and the option to toggle between a time domain plot and frequency domain could be made available. Also, the addition of an interactive visual element of a clock that can adjust the disturbance time would be a nice touch to relate disturbance time to a visual element, which was a piece of feedback from the user experience survey. Touchscreen support could also be added, which would allow mobile devices to use this online simulator also. I would also like to improve browser support by investigating known issues and resolving them where possible, such as the highlight text issue on Chrome and Edge, and improving Safari's overall performance. I would also hope to add keyboard control, so that mouse inputs are not the only method of entry, which would make the simulation more accessible. Thank you.